Hello everyone. My name is Eshan, and today I would like to talk to you about compiling programs to JavaScript. Specifically, I'm going to talk about compiling programs from languages like C or C++ to JavaScript. First, a little bit on why you would want to do something like this. You may have large code bases, such as, for example, a game engine that you would like to run inside the web browser if you, for example, want to make it possible for people to run a game inside a web page. But you don't want to put all of the effort that is required to port that code base manually to run inside a web browser. And you may want to have some help in doing the port. Or you may also have libraries that are written in these languages for things like image processing, audio processing, and various different types of applications. And you may want to use these libraries inside a web application without necessarily porting the library manually to run on the web. So how can you do this? Let's look at how a native compilation pipeline works really quickly at a high level. We start from the source code. The source code is fed through the compiler. The compiler generates machine-dependent output, which is basically the code and the data. And the linker creates a program binary out of that output from the compiler. The operating system loader knows how to load this into the memory and to point the CPU at the entry point of the program that is typically your main function. And then the CPU knows how to run the program because it knows how to execute the instructions in the program binary. However, on the web platform, things are vastly different. You start with an HTML page. The browser downloads the page and all of the other resources that it needs to display the page, and then it displays the content. And if it finds any JavaScript on the page, it runs the JavaScript. But if there is no JavaScript on the page is just displayed. So these are vastly different environments, and it seems like there is a big impedance mismatch in between these two worlds. So how can we map these two worlds together? It turns out that the answer, like many other problems in computer science, is abstractions. They can help us. Now, if you focus on the source code part of this pipeline and ignore everything else, it turns out that everything that we need for translating these programs to run inside the web browser is inside the source code. The source code is a very, very abstract and high-level description of what the program does. So let's think about what the program does, ignoring all of the details at a very, very high level. Programs can basically do three things. They can do computations. For example, they can do arithmetic, or they can copy data, which is computing an identity function. They can do control flow. For example, they can run if conditions or loops. And they can call functions. And that's basically it. And if you think about JavaScript, JavaScript can do computation. JavaScript can do control flow. And JavaScript can call functions. So maybe there is a simple way to just map these high-level operations to the equivalent operations in JavaScript and just translate the program using this very simple idea. This is what mscripten does. Mscripten is a drop-in replacement for compilers like GCC and Clang. Instead of creating a program that can run on a native CPU, mscripten creates a JavaScript file as the output. And the JavaScript file is a JavaScript program that you can run either in an environment like Node or inside your web browser. And mscripten itself is a mature project. It's an open source project. It's done by Mozilla and a vibrant open source community, and it's used for many, many commercial applications that are actually things that people depend on these days in the real world. So let's take a look at what mscripten does to a very, very simple C program as the input. Here we have two small functions. We are doing a little bit of arithmetic and a printf, nothing really too fancy. And we take this program and we feed it through mscripten, And this is what part of the output that is basically the direct translation from the input C program looks like. So you can see that some of the structure in the input program is preserved. There are two functions in the translation in JavaScript. They have names that are similar to the functions in the input C program. Some of the names in the variables, for example, the argument names are preserved. But there are other names that are popping up, such as these dollars, zeros, and ones. There are notions that you may not be familiar with, such as these ors with zeros, that in JS cause the JavaScript runtime to interpret a number as a 32-bit integer. But these are just tricks that Emscripten is playing out in order to simulate the exact same semantics that a C program has at a very, very high level. Even things like the stack and the heap that you may be familiar with from a traditional C execution environment are also emulated in this JavaScript world, all by just generating the required code for it. But this is nice and enough for a simple toy program, but how can this be enough for like a large code base, such as the example that I gave, the example of a game engine? So it turns out that you need to deal with a few other additional things on the side as well. The first step is the standard library. The standard library that you are probably familiar with if you're familiar with C or C++ is something that you basically always rely on as a part of the environment that you program in. And it turns out that if you have a compiler that can generate JavaScript from C or C++, you can also feed it a standard library written in these languages and just get it to compile the library for you without doing a lot of work to recreate the library from scratch. So this is what Emscripten has done. For C, we use the muscle libc, and for C++, we use libc++ from the LLVM project. These are both open source libraries that we just compile to JavaScript. For example, this printf function, I just copied from the same output of the same program that I showed earlier. The printf function, the original source code is coming from muscle, and it is compiled by Emscripten in the exact same way that it compiled our two functions. What about file system access? The browser doesn't really have access to the real file system. So what Emscripten does is it provides access to a virtual file system, which by default can be an in-memory file system where you have all of the data that you want loaded in memory, but it also optionally supports persistence using the IndexedDB API inside the web browser if your application requires persistent data. What about graphics? So if you think about a program that uses OpenGL, what the program is doing is it's just making a bunch of function calls. So if you take the function calls that you name as OpenGL and just re-implement all of those function calls on top of what you have available on the web, which is WebGL, you get the exact same functionality for free. So Emscripten does exactly that. It knows how to emulate two OpenGL dialects and also EGL all on top of WebGL. And this has allowed us to take full desktop 3D game engines and compile and run them inside a web browser with very, very little custom work. What about audio? Again, similarly to graphics, you can choose the APIs that you want to support, implement the exact functions that a C or C++ program would call, but just do it in JS on top of what you have available to use on the web, and get the functionality integrated with your application. And as I mentioned, this is a mature project. It's real. We have ported pretty much all sorts of different software, from like game engines to different types of programming languages to things like Vim or SQLite to compression libraries to many, many, many other software in these languages that you can think of. And you can use these as sort of building blocks to extend your existing web applications and mix and match these in very, very interesting ways. If you find this interesting, there are two related interesting technologies that I didn't really have time to go through in this talk, but I wanted to mention them at the end. One of them is ASM.js, which is a subset of JavaScript that gives you a near native performance if you want to have applications that run inside the web browser almost as fast as they run natively. And the second one is WebAssembly, which is a cross-browser binary standard for binary JavaScript modules that the browser knows how to run. And in the near future, this will be a standard output of a standard compiler that you can basically use as a cross-compiler target for any application and currently cross-compile to, for example, mobile platforms. And thanks for your attention.